And you are of course most welcome. This is Project Euler problem number 1, and the object of these videos is to find elegant solutions to simple problems, because once you get past about problem 50 on Project Euler, brute force ain't gonna help you. So we're going to go through all the problems from 1 to 100. That's the ones that Project Euler allow you to talk about, and we're going to try and find nice elegant solutions for all of them. So let's start with problem number 1. Multiples of 3 or 5. If we list all the natural numbers below 10 that are multiples of 3 or 5, we get 3, 5, 6 and 9. The sum of these multiples is 23. Find the sum of all the multiples of 3 or 5 below 1000. Okay, so the brute force solution is pretty obvious. We just do total. So we have a variable to get the total, and then we loop through all the integers between 3 and 999, because it does say below 1000. So for I in range, might as well start at 3 because obviously 1 and 2 are prime, so they don't divide by 3. We'll stop at 999. Python's a bit weird. When you want it to stop at n, you always have to put in n plus 1. I don't understand the logic behind that, but that's the way it is. So now we do the mod test. So if the integer divides by 3, well, what we're essentially saying here is if the integer divided by 3 has a remainder of 0, then we know it divides by 3. Or I mod 5 is equal to 0, then total plus equals I, and then we print off the results. Print total, and that produces the correct answer very quickly indeed, because there's only 997 iterations, but it is brute force because we are going through every integer within the range, so we need to find a way of avoiding this. Now, if you want to impress somebody who doesn't know very much about computer science, you could do the whole thing in one line. It's still brute force. It's still a very naive solution, but it looks better. So something like this. Print sum. We're going to do a thing called a list comprehension. So print sum, I for I in range 3 to 1000. I'm not putting any spaces in because I don't want this to go beneath the browser, so I don't want to run out of room. Where are we? Here. I for I in range 3000, and then you do the if statement. So if I mod 3 is equal to 0, or I mod 5 is equal to 0. This should produce exactly the same result, and indeed it does. So this is just a one-line version of all this. So as I say, if you find someone who doesn't know very much about computer science, show them this and you might impress them. You won't impress anybody who really knows their stuff though. To do that, we need a solution that avoids brute force. And there is such a solution. So let's take a look at the integers below 1000 that divide by 3, and we see they form something called an arithmetic series. All the way up to 999. There we are. So for an arithmetic series needs 3 things. 3 different values which we then plug into a formula. So we're going to find the sum of the arithmetic series. So the sum, well, we don't know what that is yet, so we'll put a question mark there. A is the starting point. What is the very first value in the series? Normally this is denoted as A0. So what is the first value in the series? It's 3. N is the number of elements in the set. So we can find this by taking the last value and dividing it by the first value. 999 divided by 3 is 333. So there are 333 integers below 1000 that divide by 3. The last one is D, which is the common difference. So we can see that every value is increased by 3, so the common difference is 3. And there we are. So you'll notice this spells out the word sand. Just remember that, sand. And here's how the formula actually works. So we'll call this sum of threes is equal to n divided by 2 times 2 times d plus n minus 1, 2 times a plus n minus 1 times d. So let's plug in all the values for 3. So we have 333 divided by 2. A here is going to be 3. N is going to be 333. And D is going to be 3. Lots of 3's. Now I'm just going to tidy this up to make sure that BibMaths is properly applied. So let's do that there. And I think maybe one here as well. Yes, I think that'll do. So that gets you all the integers, excuse me a second, that gets you all the sum of all the integers below 1000 that divide by 3. Now we need to do the same thing for 5s. So 5, 10, 15, 20, 25, 30. Now you'll notice that 15 appears in both sets. That means we're going to count it twice. And in fact, every number that divides by 15 is going to have this property. There's 30, 45, 60, all of them. So we're going to figure out a way to get rid of those. First, let's do the 5s. So sum of 5s is equal to, we'll just copy this down, it's the same formula, we're just going to change some of the values. Whoops, we need the whole thing. Right, so this time we don't know the sum yet, but A, the first value, is going to be 5. N, the number of terms in sequence, is going to be 995 divided by 5, which is 199. So let's pop this in. I'll pop that there as well, just so I don't forget. D, the common difference is 5 because we're always going up by 5, so there we are. Plug these in. This was our A, so that's 5. This was N, so that's 199, and this is D, which is 5. Now how are we going to take care of those 15s? Well, we've got the sum of 3s and we've got the sum of all the 5s. So now we just subtract the sum of the 15s. So we do another arithmetic sequence and we find the sum of all the 15s. So sum of 15s is equal to, so we'll copy this. Oh, I've made a boo-boo there. That's 199. There we go. Okay, so let's pop this down here. So what are the values going to be this time? We don't know the sum. We know the starting value must be 15. Now what about the number of terms? That's 15 up to 990, which is 66. 66 divided by 2. A is 15, D is also 15. So we have 2 times 15. This is something you could literally do on a calculator in about 1 minute. 66 minus 1, and then this one becomes another 15. And then we simply do print sum of 3s plus sum of 5s minus sum of 15s. Let's get rid of all this. And now we should produce exactly the same answer. Indeed we do. And we have used no iteration whatsoever. We've just done the same formula with 3 different sets of values, and then we've spat out the answer. So that is, I think, the best way to solve problem number 1. Join me next time for problem number 2.